Okay, we started talking about the matrix inverses last time. We started by saying that, well, in mathematics we learn about a bunch of operations we can do to our entities. We have numbers or other things, and to these numbers we want to apply certain operation. Basic operations are addition and subtraction, multiplication, division, exponentiation, and composition. 6 operations to learn. We went as far as multiplication. We spent quite a bit of time on that. We came to division, and then we are planning to spend about a month or so on that. Back in elementary school, you remember division was also a kind of a painful process. It wasn't all that straightforward to divide. Let's go back there and see what was the issue. So let's start with a simple division. Suppose you want to take a look at 2/3. How would they justify or explain concept of this fraction? You can do one of two ways. You can take 2 multiplied by 1/3, or you can take 1/3 multiplied by 2, and either way you arrive at the same answer. One thing to pay attention to is that for matrices we don't have this luxury. So the notation A over B is not going to be well defined because presumably you can interpret it as one of two ways. This can be A times 1 over B, or it can be 1 over B times A. We said matrix multiplication has a lot of properties similar to ordinary multiplication except one thing. And what was that property it doesn't share with ordinary multiplication? If you have one matrix and another one, if you want to multiply them, what is it that you have to watch out for? That they are not commutative. You cannot exchange the order, and that creates a huge amount of headache for us. So the notation of A over B cannot be used because we don't know what sense it's going to have. Is it this one or is it that one? And these are not the same because matrix multiplication is not commutative. So we have to give up this notation and build something else. We have, in practice, in some software, they actually do have two kind of division that parallel these type of things we have written. So in ordinary mathematics writing, you are familiar with A over B. Like for example, you might write 2/3. When they are typing it in line, they can write a fraction like that. When you come to linear algebra, they actually have such a thing as well, B under A. It's not the kind of division symbol you see all that often in ordinary text. Actually, I haven't seen in any, but some software, including MATLAB software, they do have such a notation. So there are actually two different divisions, and they do play their own roles, and both of them are important. Now, to get away from this kind of situation and confusion, we come and say, well, let's do something else. So we are going to use the other notation we know from algebra, that the inverse of a number can be written with that number raised to power of -1. We borrowed that notation from there, so b to power of -1 is going to mean inverse of b for us. And the month or so that we are spending is trying to figure out what that inverse is going to be. So let me just put something out of your mind right now to just give you a heads up that the situation is not going to be all that straightforward. So if I have a matrix like 2, 3, 3, 5, so something like this, B inverse, you are going to learn how to find it. And right now we are saying don't think about it in terms of component-wise operation, like the simple things you used to do with a addition and subtraction, that you just go ahead, add corresponding elements or subtract corresponding elements. Such an idea is not all that useful or used in this case, so we don't have much of a use for doing something like this. So we are going to put a big red line on that. So that's not what we are after at all. What we are after is entity. That matrix is going to be a special matrix with the property that if you take the original and multiply it with that inverse in either direction, you are going to get what? So if you multiply the two matrices, and that's the multiplication we learned over there, if you multiply them, what are you supposed to get? Identity, or 1. So this is the identity matrix, or the matrix that we just simply refer to it as a 1. Typically we write it as I. So if I want to talk about this, I'm going to write A B inverse. If this is what I want, I'm going to write it as B inverse times A. And since I know matrix multiplication is not commutative, I'm aware that these two things are totally different. So if I want that, I use that. If I want this, I use that, and I don't mix them up. So we are not going to see that fraction line anymore. It's just not used. However, keep in mind that once you go to software, these things will show their head again. Next issue that we wanted to mention, and we kind of referred to it in the previous lecture, is that not every division is allowed. So back in elementary school, they tell you this a number divided by 0 is undefined. So any number divided by 0, in fact, is undefined operation. It so turns out that there are many matrices also whose inverse is not defined, and it isn't just a 0 matrix. There are many matrices whose inverse is undefined. And we want to say that it is not just the 0 matrix whose inverse is not defined. So the problem isn't just here. That by itself becomes a major task. Given a matrix, how do you know if it has an inverse for you go to find it or not? But right now, let's just have this in the back of our mind that matrices come in two varieties. The ones that have an inverse, we call them invertible. These are things that have an inverse. And then there are other ones. We can call them non-invertible, which is kind of a strange English. Sometimes they call them singular, which might sound, again, as strange English to you. So they are not invertible, means do not have we are going to have a whole slew of red flags that's going to separate these two for us, tell us who is who, and it's going to be an important issue. Now, before we before we go into that, let's just cover some basic ideas. One of them is that, first of all, inverses that we are investigating, these are exclusively for square matrices. We are not going to deal with rectangular ones, the ones that are not square. We put them out of our mind for now. So the matrices that we are going to consider in this section, A is a square matrix. So you might call it n by n, or number of rows is same as number of columns. Its inverse, if it exists, we are going to show by A inverse. So that's going to be our notation for inverse of A. The property of the inverse is that what you expect out of it is that if you multiply it in either order, you are going to get identity. First question. In mathematics, it's quite common when you define something in a general fashion, you don't specify exactly how to get it yet, a question comes up. Would there be only one of these things, or would there be a lot of them, or infinitely many of them, and such? So the question is the inverse of a matrix describing what the inverse of a matrix is. Okay, we said sometimes there isn't any. So if matrix is singular, there isn't any such thing anyway. If the matrix has an inverse, we call them invertible. But the question comes up, is there only one such thing, or can there be several different inverses? So that becomes a simple basic theorem for us. The positive answer here is actually a theorem. So we are going to state that if A has inverse, then that inverse is unique. Let's cook up an argument like this. Suppose both B and C are inverses of A. Suppose one student worked out, find one matrix B, another student worked out, found another matrix C. What we want to say is that assuming that the students did their jobs right, that B and C have to be the same. It can't be one guy finds one thing, another guy finds something else. So suppose B and C are both of them inverses of A. Then we are assured that these two have to be the same thing. So that clears out the situation. Any two inverses have to be identical. How do we go about proving this? Now, this is going to be a little bit different from all the arithmetic we have done so far. We are making a general argument without using any numbers or anything like that. We are just using the definitions and our general logic to arrive at a conclusion without having any specific numbers in front of us. So you might feel a little bit uneasy about such statements, but try your best understanding them. So if I say B is an inverse of A, what does that mean? Well, we said inverse is a matrix that if you multiply with the original, you get identity. So if you say B is inverse of A, that means if I multiply it with A in either style, what do I get? Identity. You are also claiming another matrix C is inverse of A. So what does that mean? Same thing, is that right? So one guy found B, one guy found C. Without going into the detail of what these two people have done, assuming that they did every arithmetic right, we want to show that B and C got to be the same. So I pick, for example, I pick this statement that somebody is assuring me that the B I found, somebody is assuring me that the B that I have found have the property that A times B has to be identity. I say, okay, if that is so, if I go ahead and multiply this by C on the left, if these two are equal, then multiplying by C, they are still equal. Now we learn about a certain property of matrix multiplication. C times A times B can be written also in another way, which is what? C times A times B. We didn't prove it. That was one of the problems I asked you guys to look into it, that the matrix multiplication is associative. You can rearrange the order of operation and you still get the same thing. So these two guys are the same. Now what is C times A? The other students claiming that he found an inverse, his inverse is C. So C times A has to be what? Identity. Now we learned about the property of identity matrix. When I multiply identity by matrix, what do I get? Just that matrix, is that right? So that's got to be C. So the two matrices that we have, they're got to be the same. So the matrix inverse is unique. So let's write that again. Inverse of a matrix, if it exists, is unique. So that was a theorem for us. Again, that is a very general idea in mathematics. You try to present something new, and the first issue that comes up is how many of these things are really out there. 0, 1, 2, infinitely many, and so on. While we are on the trail of this kind of general observation that doesn't include any numbers, let's indicate some other nice properties. Suppose we have two matrices now. We keep using same letters, so ignore that previous theorem right now. Suppose A and B are invertible matrices of same size. Now we are not going to talk about size anymore. We're just going to assume that in the background that everything is taken care of, so that when we are doing things, our matrices do match. Then A times B is also invertible. And its inverse is, so here the claim, if you have two matrices, each of them are invertible, then we can guarantee for you that the product of these two is also invertible, that A times B does have an inverse. So how do you think we can cook up the inverse from the individual inverses of these two guys? What should I do? In basic algebra, if you have a number and the other number, both of them non-zero, if you want to raise it to power of -1, what can you do there? How can you bring that exponent to individual numbers? Well, that is one way to do it. What do you think happens here? Inverse of a product of matrices is a product of inverse, but something interesting happens. It's the product of inverses in reverse. That is, it's B inverse times A inverse. Okay. Product of invertible matrices itself is invertible. A times B is invertible. And that inverse is the product of inverses, but in reverse order. That order again is important. If you exchange it, it will be totally different matrix, because matrix multiplication is not commutative. So that's another theorem. Let's see, why is that true? The question is, what is the inverse of A times B? And we are claiming that this is the inverse. Let's go ahead, multiply, and see what happens. If I take that, multiply with what I got. Let's go ahead and simplify. First, due to the property of associativity, I can have this B multiply with this second parenthesis first before it multiplies A. That is, this can be written as A times B times which is what? Now I can associate these two first. That multiply B and B inverse first, then multiply with A inverse. Now what is B times B inverse? That is just identity. Identity times anything is just that thing. And what is A times A inverse? Just identity. See, it was crucial for this B to be on the left to match up against this B that was on the right, for them to essentially cancel each other, and then it lets A's to cancel each other, and then we get identity. So this guy is inverse of that. Now I'm going to leave it to you to show the other way around, that if I had written this one on the left, that is, if I had B inverse, A inverse on the left, and the original AB on the right, what do you think we are going to get in that case? Again, A and inverse, they match up and cancel each other out, and then B's have their turn and they cancel each other out, and then you get identity. So what do you think if I had three matrices A, B, C, and I wanted to write their, and suppose all three of them were invertible and of the same size, I wanted to get the inverse of their product. What would be on the right hand side? What do I write first? C, and then B, and then A. So inverse of product of several invertible matrices is product of their inverses in reverse order. And that is the thing that was kind of unexpected. We are going to have several theorems like that throughout the semester, that we do something to pair of matrices, and when we do that, we have to make the matrices flip over each other, and so instead of inverse, we are going to have other things, but this idea of reversing the order is a very common feature of many of these definitions. Okay, now we want to get ready for actually finding an inverse. And as we mentioned, the process is going to be rather laborious and extensive. We want to create a systematic way of doing it, and that systematic way is essentially built on the idea of Gaussian elimination. So we are going to use steps of Gaussian elimination, what was it we were doing in the Gaussian elimination? We had essentially 3 steps. We had, we call them row operations because we were handling rows in a wholesale fashion, all of them together. So we had, these were 3 remember, one was exchange 2 rows. Multiply a row by a non-zero number add multiple of a row to another row. We are going to go through a process that's going to use this row operation, and then we are going to explain how to use this operation to create the inverse. Let me just give an overall view of the process, and then we get down to the nitty-gritty detail of it. If you have a matrix, we want to apply any of these things that it takes until our matrix becomes an identity matrix. Okay, we can keep multiplying, adding, exchanging, and whatever until our matrix becomes an identity matrix. If during the same time we apply the same set of operations to the identity matrix, we are going to see that that identity matrix is going to convert into the inverse. So the operations that we are applying here, these are same set of operations. So we are going to see tables running. On the left hand side we have the original matrix. We go through whatever it takes to make it identity. On the right column we are going to start with an identity, apply exactly same operations, and then at the end we are going to get A inverse. Now that is a mechanical description of what we are going to do. To understand why does this thing really work and what is the logic behind it, we are going to go ahead and investigate each of these operations in much more detail, see what is the matrix representation of each operation, and check to see what is the inverse of each operation. So let's get ready for that. So simplest operation that we have is the exchange of 2 rows. Suppose I have the identity matrix here, 1, 1, 1. And I ask that we exchange, say, row 1 and 2. This type of activities are typically referred to as permutation. When you shuffle something and change the order in which they show up, we refer to them as permutation. Permutations, when you just change 2 things, like you have a deck of cards and then you just take two particular cards and exchange their location, as opposed to shuffling everything and making a big mess. If you just shuffle two things and exchange their location, they refer to that as elementary permutation. So let me call this matrix P for permutation. Now think about the physical process of having exchanged those two cards in a deck. What would be the reverse of that operation? What do you think? Suppose there was an ace on the top and a king at the bottom, and you just exchange it, and somebody says, I want that original virgin deck. What do you have to do? Just exchange exact same two things. Is that right? Exchange. Now, I'm going to ask you to make a wild guess. What do you think is the inverse of this matrix? We haven't calculated the inverse of anybody yet. But again, I ask you to take a wild guess. This one, think about it as a deck, two cards of which were shuffled. Okay. Now, or the act of the shuffling itself. Now I'm asking you to guess what would be the inverse of this matrix. Now, act of exchanging row 1 and 2, that is exactly what was captured by this. So our guess would be the exact same matrix will actually act as the inverse of itself. Kind of looks peculiar, but let's see. What was property of inverse? The property of inverse is that if I multiply them, I have to get identity. Now, whoever you want to put first and who you want to put second, it doesn't make any difference because these two matrices are the same thing anyway. But let me ask you to multiply them. How did we say we multiply two matrices anyway? We take, let's start with P times P inverse. I have to multiply this row with that column. What am I going to get? Is that right? Because that one shows up in the same location here. What if I multiply it by any other of these columns? This 1 hits a 0 here, hits a 0 here, so I'm going to get 0 in both cases. Now, let's consider the second row with the first column. What do I get now? 1, this 1 hits that 0, so I'm going to have a 0, and now, second row with the second column. 1 times 1. The second row times the third column. And then 1 hits a 0, 0. Now, third, that wasn't for third anyway. So when I multiplied by this, obviously I get 0 here. Multiply by the second, I get 0. By the third one, I get my so if I take the identity matrix and exchange two rows of it, what I create is something that I call a permutation matrix or elementary permutation matrix. Such matrices have this nice property that their inverses are exactly copy of themselves. You don't have to spend any energy to find them. You just copy that same thing. They are just their own inverses. Now, what if I had a matrix that wasn't just identity or something? Suppose I have a matrix with some arbitrary components in it, D, E, F, G, H, I. Suppose I multiply this matrix on the left with a permutation matrix, 0, 1, 0, 1, 0, 0, 0, 0, 1. Let's just go ahead and multiply this, see what is the benefit of this multiplication, or what is the net effect of it. If I multiply this row with any of these columns, who's going to be targeted and what's going to show up on the top row. 0, 1, 0 times any of these columns, who's going to be picked out? The second row, is that right? The D, E, F is going to be picked out. Everybody sees that? So 0 times A, so that first and last don't make any contribution. Only the second entries are picked out. Now if I take the second row and multiply with these columns, who gets picked out now? The first one gets picked out, so I'll get my A, B, C. Now the third row was untouched. It's a part of the original identity. When you multiply, it doesn't do anything to your matrix, just picks out what was there to begin with. So G, H, I. So this particular permutation matrix was created out of exchanging row 1 and 2. So I might call it P12. So P12 is a permutation matrix that is created out of exchanging row 1 and row 2 of identity. If I take that permutation matrix, multiply it on the left, that permutation matrix sitting on the left, times an arbitrary matrix, the net effect is what? Yeah, is exchange of now there isn't anything special about row 1 and row 2, or the fact that these are 3 by 3 matrices. They could have been 100 by 100 matrices, and I might have targeted row 23 and row 52. I wanted to exchange them. I create a permutation matrix where row 23 goes to row 52, or row 52 comes back to row 23, and whatever that matrix is, if that is multiplied by an arbitrary matrix, is going to exactly exchange those two locations. So Pij plays the same okay. So by now we have learn one part of the game. Okay, let's go back to the row operations. Row operations that we had, one of them was exchanging the two rows. Exchanging rows can be captured by matrix multiplication. Nice thing about this matrix multiplication is that its inverse is very easy to get. In fact, its inverse is just itself. So what we have for this particular matrix is that its inverse is the easiest we could expect, is just itself. Now we go to the next type of activities we had with Gaussian elimination, and see if our luck still holds and we can find the inverse of another matrix that is hopefully just very easy. And one of the matrix activities that we had was multiplying the row with a number. So row operation number 2 multiply a row by a number. Now we learned this as an activity. Take a matrix, say double the first row or quadruple the fifth row or something. A nice idea comes to our mind that those activities can be captured by matrix multiplication. And hopefully they have easy inverses, so we can play with those one little step at a time instead of having one gigantic matrix that we want to invert all at the same time. So we are trying to break the job to very small pieces we can manage. Let's play a game. Suppose we have a matrix and its entries are, again, let's just keep it to size. Suppose I want to double the third row. Okay, I want to do an activity here which is equivalent to double third row. Let's see if that action can be obtained by matrix multiplication. So I ask, is there a matrix that if I multiply with this guy, its net effect is double the third row? Well, so okay, first row I don't want to touch it. Second row I don't want to touch it. So what do you think is a likely matrix here that leaves the first and second row untouched? Now, that portion of the identity matrix is the best thing we could use because it just doesn't do anything, doesn't touch anything. So if I had 1 here, if I take 1 multiplied by these guys, the first row is just copied over. 0, 1, 0 multiplied by these columns, D, E, F are going to be copied over. Now my expectation out of the third row, if such a thing at all is possible, is to double everybody. So what do you think I should have on the third row, if that is possible, to double? 0, 0, 2. So we check to see well, it easily works because these don't care about what you had up there, doesn't create any tangling. 2, well, that's supposed to multiply the elements in this row, so all the elements double up. So we see that multiplying a row by a number can be captured by a matrix multiplication. Now, the idea of inverse is that you want to undo things. And the question is, can I go from here back to the original? That is, if I had A, B, C, D, E, F, 2G, 2H, 2I, can I force it to go back how it was? By an operation. That's the matrix multiplication, and hopefully it just comes to our mind easily like that one and plays the role of the inverse of that guy. So who do you think this one is? So I want to question, what is it? 1, 0, 0, 0, 1, 0. Again, these two rows not touched. The third row, we want to go back, we want to cut it down to size. So what should I do here? 0, 0, and 1/2. So this matrix multiplication, that let's go call it M for multiplication. Multiplication of third row by 2, but let's just call it M. This is another matrix multiplication. Well, what's the relationship of these two? 1, 0, what do you think I'm going to get if I multiply them? It better be like that, because this is bringing it back to the original. This was taken into the right hand side. These are opposite operation. If you multiply them, you easily check that this is identity. And it doesn't matter in which order you multiply them. If it's 2 and a 1/2 or 1/2 and a 2, you get the same thing. So multiplying a row by a number can be captured by matrix multiplication, and the inverse of that matrix multiplication is just very easy. Whatever number you had here, just replace it by its inverse, and you are all set. All that is left for us to do is the matrix operation of type 3, adding a multiple of a row to another row. And let's wait for that for Friday. Okay, so these are the problems you want to do. You can check it up on the internet.